Analytical geometry, it's a paper 2 section. And it's the section that comes after statistics. So question 3, question 4. Question 3 is your grade 11 analytical geometry. And then question 4 is your grade 12 analytical geometry. Both questions weigh around the same marks, which is plus minus 20. So, which automatically shows you how important it is for us to remind you of the basic concepts in analytical geometry. Because as I'm saying to you, you're going to have 2 questions in analytical geometry. Question 3, which is going to be based on grade 11 Euclid analytical geometry. And then question 4, which is going to be with regards to grade 12 analytical geometry. Can I please check in with a thumbs up if people can hear me, or I've just been speaking alone this entire time with a thumbs up or thumbs? I don't know. Can you guys hear me? Right, I'm getting thumbs up. That's good. So, as I said, 2 questions. You will notice that there is nothing much that is changing with grade 12 analytical geometry. The only thing that is changing much is in grade 11, you would have noticed that we were working more, or we were working with um, line segments. So we're working with lines. Generally, your biggest worry was how to calculate the equation of a line segment using y is equals to mx plus c. That was your biggest worry in grade 11. And then if you had the smartest examiners, they would have started bringing in a little bit around circles in the grade 11 analytical geometry, where they're going to ask you a certain line segment. If there was a circle around it, how would it be a tangent and all those things, etc. But so just to get started again, we're just going to have a look at concepts that you should have already grasped from grade 11 and check if you still remember those, right? Because again, it's pointless if I'm just going to start with grade 12 analytical geometry, because it's only half of the total marks that you're going to have in your total paper in analytical geometry and stuff. So, right. So we know that in grade 11, you were looking at a straight line, most likely. Again, when I say straight line, it doesn't mean that you're going to have a Cartesian plane and you only have one straight line. It can be multiple straight lines. It can be straight lines forming shapes and etc. And we're going to get to talk about shapes just in a minute. But for now, just remember that in grade 11, your biggest worry, or what you're focusing on, is working with line segments, right? Which are straight lines. And we know that the equation of a straight line is given by y is equals to mx plus c, where y obviously is the y value, m represents the gradient of that particular line. Some people call it the slope, and then the x represents the x value within the particular line, and then the c represents, it's a constant, it represents the y-intercept. I tried to indicate on this side right here that your C represents the y-intercept. Y-intercept, remember, it's basically the point at which that particular line will cut the y-axis. That is what we're talking about when we talk about um, the y-intercept. Just remember that. So again, because when you have to determine the equation of a straight line, you need to understand gradient, right? So that's the first thing that I'm going to talk about. Again, remind you of. So gradient, again, we're talking about the change in y over the change in x. We want to find out how are the y values changing with respect to the change in x values. So you have this nice equation here that we've been using from even in grade 10, where we talk about the gradient of a line segment AB being the change in y over the change in x. So you want to see how the y values are changing. You take one y value, you subtract another y value, because remember, we can calculate the gradient of a straight line between 2 points, right? So that means you need to have 2 points, A and B, for example, in this case, where you're going to take the y value of the two y values, subtract them, and the two x values, subtract them. But the important part is remembering the fact that you need to be systematic with your subtraction. What do I mean when I say you need to be systematic with your subtraction? So if we can have a look at the equation, it specifically says y2 minus y1 over x2 minus 1 minus x1. So this automatically tells you that if you take the y value of point B and subtract the y value of point A, similarly on the denominator, you need to take the x value of the point that you started with and subtract the x value of the point that you subtracted afterwards. So in this case, if I'm looking at the line segment AB, I've named point A as x1, y1. I've named point B as x2, y2. So that automatically tells me that every time I start with this one, I'm going to take, let's see. Can you please mute yourselves, guys? Please mute yourselves. Okay, let's just leave that. Right, so you have two lines. You have a line segment AB where, again, you take the y value of 1 minus the other one and the x value to do the same thing. I was just reminding you that don't forget that you can't say the y value of A minus the y value of B, and then you start with the x value of A minus B. You can't swap things around. So you have to be consistent. If you start with B minus A, you need to also, for the x value, start with B minus A. I think that makes sense. And then here I was just making an example to say if I have, for example, a line segment AB right here, I am choosing my 2's to be the the point B, and then my A's to be my 1, basically. So that I can say my Y2 minus my Y1 on this other side, as you can see. And then I can also say my X2 minus my X1. And then that's it. Then you're going to get the gradient of the line segment AB. Then we come to remind each other about how the gradient is supposed to be when you have an increasing function versus a decreasing function. What is the decreasing, increasing function? We're just talking about the straight line, whether it's going up, that's increasing, or it's going down, that is decreasing. So just to show you examples, if you look at the line segment CD on the screen, this is a decreasing function or a decreasing straight line, because remember, on the Cartesian plane, we start reading off values starting from the right-hand side, starting from the left-hand side towards the right-hand side. So we always start on this side, which is the left-hand side, and then you're going to this side, which is the right-hand side. So if you look at C, C is higher up, D is lower down. So therefore, that shows you that the line segment is decreasing. And for a decreasing line segment, we expect the gradient of that function to be negative. So if you're doing a calculation and you're looking at the line segment that you're working with, the line segment is a decreasing function, but you're getting a positive answer, then you know that you are wrong. So you need to fix your signage. Something is wrong with the way you've allocated signs. Similarly, if it's an increasing function, if it's a straight line going up like this, then you know very well that it's supposed to be giving you a positive gradient. So when you calculate the gradient of such a line segment, you are expecting to get a positive answer. That is just increasing versus decreasing functions. That's the one thing that you need to note. If you have a line segment that is an increasing function, you're supposed to get a positive gradient. If you have a line segment that is a decreasing function, you're supposed to be getting a negative gradient. If that is not happening, definitely something is wrong with your calculation or your signage. You need to fix your signs and pay careful attention to them. Then we speak about the gradient of horizontal versus vertical lines. What is a horizontal line? A horizontal line is the blue line that you're seeing on the screen. It's a line that runs parallel to the x-axis, right? So that is a horizontal line. So we say that a horizontal line does not have a change in the y values. How do we know that? If you look at this Cartesian plane that I've drawn right here, and you see the blue line segment, you can see that it's on the same y value. Right? If this was -4, then this line would be y is equal to -4, which shows us that there is no change in the y values. So the y values are remaining the same throughout. So what does that mean for our gradients? That automatically means that you're going to have a gradient of 0. Why? Remember when we defined gradient, we said gradient is the change in the y values divided by the change in the x values. So if the y values are not changing, just like in this case, when you look at a horizontal line, the y values are not changing, you're on the same y value, that automatically means that the change in y is going to be 0, because there is no change in the y values, versus we don't care at this point whether you have a change in x or not, because 0 divided by any number is always going to give you a 0. So what is the conclusion that we are making? The conclusion that we're making is that if you have a horizontal line, the examiner will not necessarily tell you that this is a horizontal line, but you're going to see that this is a horizontal line because it's going to be a line parallel to the x-axis whose y values are not changing. It's on the same y value, and its equation is going to be something like y is equals to a number, like y is equals to -4. So that is a horizontal line, and because there is no change in the y values, automatically it's going to have a gradient of 0. So that you're supposed to know at this point. You are supposed to know. Then we are looking at a vertical line, right? We started the horizontal one. Now let's look at the vertical line. So if I have a vertical line, what is a vertical line? When you're talking about a vertical line, we're talking about a line that is parallel to the y-axis. Remember, I said a horizontal line is a line that is parallel to the x-axis. Vertical, it's parallel to the y-axis. So if you have a line that is parallel to the y-axis, that line is a vertical line. So a vertical line will have the same x value because since it's parallel to the y-axis, it's going to sit exactly on the same x value. If this is x is equals to 2, for example, that line is going to sit on x is equals to 2. It's not going to change its x values. However, what we can see from the screen is that the y values are changing because this line starts somewhere here, then there's a y value here, there's a y value here, 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 here. So you can see that the y values are actually changing. So there is a change in y. That's what we can acknowledge, right? Again, what does that mean for the gradient? We go back to, we know that the gradient of a function is given by the change in y over the change in x. Do we have a change in y? The answer is yes, because the y values are changing for a vertical line. However, do we have a change in x? No, we do not have a change in x because this line is exactly on the same x value. So because the line is exactly on the same x value, that automatically tells us that there is no change in x. And that is why I substituted 0 here as my change in x. Since we have a change in x of 0, if you take a calculator and take any number, whether it's a billion, trillion, or gazillion, if you take any number and divide it by 0, you're going to get an undefined. You're going to get a math error, which means that the gradient of a vertical line is undefined. Or someone can say there's no solution to it. It doesn't exist. It's undefined. So that is the conclusion that we're making with regards to vertical lines. For horizontal lines, we know that the gradient is 0. For a vertical line, the gradient is undefined. Why is it important for you to understand this? Because again, you are going to be assessed on your grade 11 knowledge, and it can also be integrated with your grade 12 knowledge. So an examiner can tell you something like the line y is equals to 4 is drawn, wada, and then they just keep on telling you something, then you're just supposed to understand that, oh, actually, the line y is equals to 4 is supposed to be a horizontal line. How do I know it's a horizontal line? Looking at the equation, y is equals to 4, that is telling me that it only has the y value 4, but the x values are changing, so it's a horizontal line. If the examiner tells you that you have the line x is equals to 2, like this one, you know that, okay, this line is actually sitting only on the x-axis, so it has to be a vertical line. Or the examiner can still tell you you have a certain line that is parallel to the x-axis, or you have a certain line that is parallel to the y-axis, and automatically from that wording, you're supposed to understand what type of a line are they talking about. Is it a horizontal line or is it a vertical line? This really, really, really will help you again if you understand the type of line that you're working with, especially when you speak about things like horizontal distance, vertical distance, and etc. But we're going to get there. For now, what we're focusing on is understanding the gradient of a function, right? Understanding the gradient of straight lines. We started by defining and explaining how to calculate gradient. how the gradient differs between an increasing function and a decreasing function, and how the gradient also differs between a horizontal line and a vertical line. These are things that you must know when you're doing your calculations. These are things that should be at the back of your mind. You should have expectations as to saying, if I'm calculating the gradient for this, I'm supposed to get an answer like that. And then that is the conclusion that we're doing with vertical lines versus horizontal lines. Before I move on, is everything that I'm saying making sense? Are you still with me? Right, yes. Perfect. So now we're moving on to what we call collinear points. What are collinear points? You need to remember this. So when we talk about collinear points, we talk about points that lie on the same straight line. So if you can have a look at the line segment ABC, that is one straight line that has three different points. So the point A, B, and C, we call them collinear because they lie along the same straight line. So an examiner can give you a question or a statement and say, the point A, give you the coordinates, B, give you the coordinates, C, give you the coordinates, say those 3 points, they are collinear points. And then the examiner expects you to do something about that. What should come to your mind is that, okay, when I'm talking about collinear points, I'm talking about points that lie along the same straight line, right? And now what does that mean? If these 3 points are on the same straight line, that means the gradient between any 2 of these points are supposed to be the same. If you can look on the screen, I calculated the gradient between AB and I called that MAB, as you can see here. I calculated the gradient between B and C, that is MBC. And I also shown that you can calculate the gradient between A and C, which would be the gradient of AC. All these 3 gradients are supposed to be the same. And why are they supposed to be the same? It's because these 3 points are on the same straight line. So the same straight line will have the same gradient, right? Because in this case, again, keyword, it's a straight line. So the gradient is supposed to be the same throughout. It's not supposed to be changing. So it doesn't matter whether I calculate the gradient between point A and point B, or between point B and point C, or between point A and C. I'm still going to get the same answer. And that is very crucial and key, especially we're going to do one of the questions where you need to figure out coordinates for a certain point, etc. So it's very crucial to understand the relationship between collinear points, because understanding that, me calculating the gradient of AB, I'm going to get the same answer as calculating the gradient of BC, and I'm going to get the same answer as calculating the gradient of AC. That automatically is like a starting point in a question that an examiner can give to you. For now, just keep in mind that when you have collinear points, you have points that lie along the same straight line, which means that for between any 2 points, you're going to get the same gradient. Just keep that in mind. So I wrote on the side that the gradient of AB is the same thing as the gradient of BC, which is the same thing as the gradient of AC. You will see again in one of the questions that I'm going to show you, you might have coordinates for A and B, but not, maybe the x coordinate for C is not there. But because you understand that the gradient between AB and BC is the same, you can use that relationship between the gradients to actually figure out the answer. But for now, for revision purposes, collinear points are points along the same straight line. The gradient between any 2 of those points will be the same. Then we move on to parallel lines, right? Remember, what we're focusing on now is still gradients. We're still talking about gradients. So we know that the gradient of parallel lines is the same, because we know 2 lines that are parallel will never meet. They are lines that have the same slope. Literally, they are moving. They sort of like they have the same slope. So the gradient between parallel lines is the same. That you must also know, because then examiner can say, there's a line drawn parallel to a certain line segment. Determine the equation of that line if it's passing through a certain point. So understanding that the gradient of parallel lines is the same means that you can already figure out the fact that I don't need to have 2 points for the other line segment if I have the gradient of the other line segment already, because the two gradients are the same. So these are the relationships that you must keep in mind for any question that comes to you, or any question that they bring to you. So it's very, very crucial that you understand this. Gradients of parallel lines is the same. The moment they tell you this line is parallel to this, the first thing that I want you to think about is the gradients. How are the gradients comparing? The gradients are the same. So that's how I wrote on this side. The gradient of AB is equal to the gradient of CD. In this case, the reason is because they are parallel lines, right? And don't forget to write the reason, especially if they've given you the gradient of AB, and then you're saying the gradient of AB is equal to the gradient of CD. Give the reason. It's very important. Like in Euclidean geometry, tell us why the gradients are the same. So you have to write the reason, parallel lines. Then parallel lines and perpendicular lines, right? For perpendicular lines, we know very well that in this case, the gradients are not equal, but we know that the product of these gradients are supposed to be giving you a -1. Hence, I wrote here that if I have two line segments, like you can see here, I have the line segment AB, I have the line segment CD. If I take the gradient of AB and multiply by the gradient of CD, I'm supposed to be getting a -1. That is standard. Some math genius did the calculations and always gave them a -1. That's why we're saying if you take the gradient of AB, multiply by the gradient of CD, or the gradient of any two perpendicular lines, if you multiply those two gradients, you're supposed to be getting a -1. Why is this one very, very important? You will see when you start doing grade 12, analytical geometry, there's a whole lot of parts around determining the equation of the tangent to the circle. You know very well that if I have a circle here, think about it. If I have a circle here, and this is supposed to be my tangent, right? You know that the tangent will always be perpendicular to the radius, right? Or the tangent will always be perpendicular to the diameter. So if you can calculate the gradient of the radius or the diameter, automatically you will have the gradient of the tangent, right? Because we know very well that the tangent and the radius are always going to be perpendicular. So that's why it's very important to remind you of this, because you will be expected to calculate or determine the equation of the tangent to a circle. How are you going to understand or know its gradient? You will know its gradient because if you can calculate the gradient of the radius or the diameter of the circle, you can automatically figure out the gradient of the tangent. I hope that is clear. Which is yes.
Sorry, ma'am, to disturb, ma'am. So, ma'am, if we have a diameter instead of a radius, so do we still use the same reason?
Yes, it's still the same reason, because we know very well that a tangent and the diameter are gonna always be perpendicular to each other at the point of tangency. So if you know the gradient of that diameter, you can automatically figure out the gradient of the tangent because
Okay,
they're
ma'am. Thank
perpendicular
you.
to each other. No worries, perfect. And then I wrote on the side to remind you that, again, if I take the gradient of AB multiplied by the gradient of CD, I will get -1. So what I was saying with perpendicular lines is that if I multiply two gradients of two perpendicular lines, I'm supposed to be getting a -1. Understanding that is crucial, as I was saying, for your grade 12 analytical geometry, because you will see that for your grade 12 analytical geometry, we're going to be studying circles and lines. So it's going to be circles and lines combined. So obviously, we want to take each other through everything else, but now part of what you are expected to do is to determine the equation of a tangent to a circle. Then I'm saying, what is the relationship that we use in that case to determine the equation of that particular tangent? We know that if there is a circle around here, we know very well that this is our tangent and this is the diameter. So the diameter and the tangent are perpendicular to each other at the point of tangency. That's what we know from the theorems that you've studied. So if we understand that the relationship between the diameter and the tangent at the point of tangency is perpendicular, then we know that we can use this idea around perpendicular lines to say, if I can get the gradient of the diameter, I can basically figure out the gradient of the tangent because of this relationship of saying if I multiply the two gradients, I'm supposed to be getting a -1. And don't forget the reason. It's perpendicular lines, but you will see when we get to your grade 12 analytical, we're going to just say it's also acceptable to say tan perpendicular to radius. This is also acceptable because it explains why you're saying you are enlisting the gradients as such. And then I made an example to say, if I understand the fact that the gradient of AB multiplied by the gradient of CD is -1, most likely in my exams, I wouldn't necessarily substitute like this and say MCD equals -1 and try to solve for MCD. You could, because it still will give you the right answer. But one thing that I knew was the fact that if the gradient of AB is 5, the only thing that I have to do to get the gradient of CD, if they're perpendicular to each other, is to, 1, change the sign. So if this sign is a positive, this is going to be a negative gradient, right? And then, similarly, I'm supposed to invert. What do I mean by invert? So if I give you A over B, you must give me B over A. If I give you, just erase this. If I give you B over C, you must change to C over B. So in this case, 5 is the same as 5 over 1. So I'm going to change this to 1 over 5. So no one is going to penalize you for saying the gradients like this. Instead of doing the calculation, no one is going to mark you wrong if you say the gradient of CD is -1 over 5, and the reason is perpendicular lines. This is highly acceptable. It saves time, and also if you really would like to do it, that's very much acceptable. So just to check if you get my idea, if I have two line segments, A and B, and one of the gradients is 2, what is going to be the other gradient?
-1 over 2.
-1 over 2.
Perfect. So it's going to be -1 over 2, right? What if I have -3 over 4 as a gradient? What is going to be the other one?
4 over 3.
Was it 4
4
over
over 3. Perfect. What if I have 3 over 2? That is negative.
2 over 3.
Positive 2 over 3, right? So you get the idea. It's always going to be like that because if you put a multiplication sign in between, this is always going to give you -1. This is always going to give you -1. And this is always going to give you -1. So that's why we just say, instead of doing the calculation, of which you could if you'd like to, no one is saying you can't or you're not allowed to do it, you can, but it's just saying if you want to save time, if I'm telling you that the gradient of one line segment is 2, just tell me automatically the other one is the inverse. Just do the inverse. I hope that is clear. So that is the gradient of perpendicular lines. That's the relationship between the gradients of two perpendicular lines. And then we also have to remind you that in grade 11, you were introduced to another way of calculating the gradient of a function or a straight line, which was using the angle of inclination, right? This comes from your trigonometry, where, again, if you have a proper look, if you have a look at, I don't know, let me just do another one so that you can see. So if I have the Cartesian plane like this, and I have a line segment like that. The first thing that you need to remember, or that I need to remind you, is the fact that the angle of inclination is an angle that is drawn from the positive x-axis in an anti-clockwise direction. Keyword, anti-clockwise, guys. In an anti-clockwise direction. So it's always from the positive x-axis in an anti-clockwise direction to the line segment itself. This we call an angle of inclination, theta. This is not an angle of inclination because it's not drawn in an anti-clockwise direction. This is clockwise. So the angle of inclination, theta, is always drawn from the positive x-axis in an anti-clockwise direction to the line segment itself. So the expectation is that you also will understand that even if I give you a line segment like this, if, for example, I draw a weird shape such that I have this as my line segment and that's it. And I say to you, determine the inclination of that line. Remember, in analytical geometry, we do a lot of construction. So the expectation would be that you should understand that you should construct a dotted line like this. That is going to be a continuation of that line so that you can get to the point of, again, applying the principle that when we talk about the angle of inclination, we talk about an angle between the positive x-axis in an anti-clockwise direction, we just use an actual line, in an anti-clockwise direction to the line segment like this. So this would be an angle of inclination theta. Do not be confused when, again, you have a line segment like this one that doesn't get to the x-axis. It just tells you that, hey, you need to draw like the line further. Even though it's not a continuous function, you can still draw the line further so that you can see for yourself where the angle of inclination would be. That's technically it. Because remember, technically the angle of inclination is the same thing as if I was to move, because this is my x-axis, right? This is the x-axis. If I was to shift the x-axis and shift it somewhere here, the angle of inclination would basically be this. Again, let me just show with another color. The angle of inclination would be this angle here, which again, if you move the x-axis downwards to get to the line, you're still going to see that it's an angle that is made by the positive x-axis, again, with the line itself. Someone has raised their hand. Yes, now you can speak.
Ma'am, can you show us how we would do it if the graph was negative?
Negative. Okay, that's a good question. Let me show you. So if you have a line segment like this, is that what you're asking, Nari?
Yes, ma'am.
Okay, so the rule still applies from the positive x-axis in an anti-clockwise direction to the line segment itself. So this would be your angle theta. It would be an obtuse angle. Is that making sense?
Yes.
Okay, so keep in mind all the time what you're thinking of, what you're thinking about is you are drawing or you are getting the angle from the positive x-axis in an anti-clockwise direction. Anti-clockwise, guys, is in the opposite direction from the clock. In an anti-clockwise direction to the, what you call, to the line segment itself. Olwetu, you can speak.
Hi ma'am, please repeat what you just said about the negative water at Ishangzwang.
Okay, no worries. So we're saying it doesn't matter whether your line segment is a positive line segment or a negative line segment. So what you're saying basically that it doesn't matter if it looks like this or like that. It doesn't matter because if it's the purple one, if it's a positive line segment, still we are saying the angle of inclination is drawn from the positive x-axis to the line segment itself, like this. So this would be your theta for the purple one. For the blue one, the same rule applies. You draw your angle of inclination between the positive x-axis in an anti-clockwise direction to the line segment itself. So this would be your angle of inclination for the purple one. So it doesn't matter. Just stick to the rule. You are drawing your lines, your angle of inclination from the positive x-axis to the line segment itself in an anti-clockwise direction. And the reason why this is important for me to mention is because you will understand, it's because you will understand that from Euclidean, not Euclidean, from trigonometry, when what you were taught was that when I have an angle in an anti-clockwise direction, that is a positive angle. Do you guys still remember that? That if I was to draw an angle in an anti-clockwise direction, that angle is said to be a positive angle. That is why our Cartesian plane, it says 0 and 90 degrees here. It doesn't say 0 and 90 degrees down here because these are negative angles. This would be negative 90. So when we draw angles in an anti-clockwise direction, that is positive angles, or those are positive angles. Again, 180, 270 like this. Those are positive angles. So if you were to do this instead, if you were to think of your angle of inclination as this is in a clockwise direction and this is a negative angle. That would be a negative theta. You will see where this applies when I'm doing calculations with you using tan theta is equal to m, and it would all make sense. So is that clear? The expectation with the angle of inclination, where we measure it from. Because it doesn't mean that any angle that you see on the diagram is an angle of inclination. No. Some examiners will try to check if you understand the concept of angles of inclination by manipulating things. I could give you an angle and say this is an angle 120 degrees. Then I say to you, determine the gradient of the line segment. If you say tan 120 and you say that is the gradient, you're wrong, because that is not the angle of inclination. Instead, this is the angle of inclination, which is 60 degrees. Oh, no. Is it 60? Yeah. So the other thing I wanted to say was, again, just for interest sake, in case you are interested, the reason why we say this is because, yes?
Can I please ask? So
Yes?
basically, the angle of inclination can only move in the anti-clockwise direction,
Yes,
because if
only.
it moves in the clockwise direction, the what you call the theta is going to be negative.
Yes, it's going to be negative theta, and I'm going to show you that.
Okay, thank you.
No worries. I'm going to show you. So as I was saying, how we come to this conclusion, right, is the fact that if I have this this blue line segment right here, and we want to find out why do we get to this conclusion. So we are saying, if I was to draw a line parallel to the y-axis, like a line that is vertically straight downwards like this, to form a right angled triangle, like this. So that's why we basically draw it, to show you that if I was to have another line that is parallel to the y-axis, such that I have a right angle triangle, and then again, keep in mind that this is my theta right here, which is my angle of inclination. If I move from here to here, is that a change in x or a change in y?
Change in x.
It's a change in x, right? Now, if I move from here and come here, is that a change in x or a change in y?
Change in y.
Change in y. Well, generally for the change in x, you want to move from here to here, but still it's the same thing, this line here. So now we are saying, if I was to check when I look at the side that has change in x in it, is that side the adjacent or the opposite or the hypotenuse of this angle theta?
It's adjacent.
It's adjacent, right? And then when you look at the other side, change in y, is it the adjacent or the what is it? This one.
Opposite.
It's the opposite.
The
right?
opposite.
Perfect. So we wanted to find a ratio that is going to accommodate adjacent and opposite. And the only ratio that could do that is tan, because we know that tan is the opposite over the adjacent from the Sokatoa. The opposite over the adjacent. Now, my question is, what is the opposite? Is it the change in x or the change in y?
Change in y.
Change in y.
Change in y.
And then the adjacent?
Change in
Change
y.
in x.
Change in x. But then now, do you remember that we said if you want to calculate the gradient of a line segment, you say change in y over change in x. So we basically then said, oh, this is actually the gradient of the line, because that's how you calculate the gradient of a line segment. You take its change in y divided by the change in x. So that's how we therefore made a conclusion and said it means that tan of that particular angle, which is the angle of inclination, is supposed to be equal to the gradient, which is m, because of this relationship that we've observed above. And that is why I'm reiterating the fact that it is only and only possible to work like this if our theta is in an anti-clockwise direction, which makes it a positive angle. And again, it makes everything true when you look at this sketch right here. Again, that is for interest sake. But again, it's to make you guys understand the angle of inclination. What is it? So angle of inclination, we are using it to calculate the gradient of a function, as you can see. So if I know the angle of inclination, I automatically will know the gradient because I can say tan of that angle of inclination, and then I'll get the gradient, and that's it. And then I've indicated here that tan theta is equal to the gradient of AB, where theta is the angle of inclination of the line AB itself. So it has to be the angle of inclination. It's not just any angle on that particular line. Gabriela, you can speak.
Oh, good evening, ma'am. Could you
Yes.
like re-explain like why we use tan theta equals n?
Right, no worries. So it's all about when you do this, right? You have the line segment. The line segment that you have is the blue one. That's your line on the Cartesian plane. Then we are saying, picture this. Picture that we draw another line that is parallel to the y-axis, which is the purple line. That line is parallel to the y-axis, right? How do we know? It's because it's perpendicular to the x-axis, right? You know that the x-axis and y-axis are perpendicular to each other. So for the purple line to be parallel to the y-axis, it means that it has to be perpendicular to the x-axis, right? So we are doing that because we are just trying to form a right-angled triangle. I hope you can see my nice right-angled triangle. So if we do that right-angled triangle, the angle theta, the angle of inclination theta becomes the angle inside that triangle, right? Then we say, looking at where I have placed my angle theta, the side change in y is the opposite of that angle because it's literally facing that side. So it's the opposite. And then change in x is the adjacent because when we talk about the adjacent side, we talk about the side where the angle is sitting at. So now we are saying which ratio allows us to substitute an adjacent and an opposite. We said that is tan, right? Because cos and sine need the hypotenuse. We don't have the hypotenuse on this diagram. We only have the adjacent and the opposite. So we are saying tan, we know that it's the opposite over the adjacent. Opposite in this case is our change in y. Adjacent is the change in x. So change in y over change in x is how we calculate gradient. So automatically that tells us that, oh, actually, this gives us the gradient because tan is giving us change in y over change in x, which is similar to the gradient. So that's how we therefore end up saying tan theta is equal to the gradient of the function, right?
Okay.
Is that making sense?
Yes, it is. Thank you.
Right, perfect. So the key thing that you're supposed to be taking from this explanation is how to look or see or figure out the angle of inclination. That's technically that. So if you know where the angle of inclination is supposed to be at on a line, you are halfway there. This was again me trying to show you that it's not going to be one line segment that they give to you. You guys are stronger now. We can handle multiple lines on the same diagram. So they can give you a triangle ABC, but in your mind, you're not necessarily viewing this as triangle ABC. You are viewing this as line segment AC, line segment AB, line segment BC. And all the rules for a line segment apply because these are straight lines. This triangle is being formed by straight lines. So here you can see I've extrapolated or I've lengthened the line to show you the angle of inclination for that line. You can see the angle of inclination beta for the line BC. You can see the angle of inclination theta for AB. And again, the same rule applies. So the same rule applies. The rule sticks to being you move from the positive x-axis all the way to the line segment itself. Well, in this case, this doesn't really matter because, yeah, but either way, that's technically that. Yes.
So, then let's say the gradient of the line is negative. Do we think of it as, okay, wait, let's say the angle of inclination is more than 90 degrees. Do we think of that as a negative gradient or?
Right, yes. So I was gonna show you again that on the question, but it's a good thing that you asked so that we can explain it and get it out of the way, maybe. So if you can have a look at this, okay, let me just draw other line segments. So if you have a look at, again, let's say you have a Cartesian plane, right? We should be able to reason this out. So if you look at this line segment here, this line segment has the angle of inclination theta, which is less than 90 degrees. Do we all agree that this angle is less than 90 degrees?
Yes.
Okay,
Yes.
so looking at this line
Yes, ma'am.
segment, is it an increasing or a decreasing function?
Increasing.
What is the
Increasing.
It's an
expectation with regards to its gradient? Is it supposed to be having a positive or a negative gradient?
Positive.
Positive.
So automatically, we can conclude that if you are having an angle of inclination that is less than 90 degrees, automatically your gradient is going to be positive. Because if it's a line that becomes greater than 90 degrees like this, so if it gives you, if you have an angle of inclination that is greater than 90 degrees, then you can see how the slope or the line itself, it's changing from being a positive line segment to being a negative line segment. So that is automatically going to give you a negative gradient. But again, when I'm doing the calculation, I'm going to tell you this is why you're getting this. And when you get this, you must do that. But just to answer your question, yes, if it's an angle less than 90 degrees, you're going to get a positive gradient because of how the line segment would look like. If it's an angle that is above 90 degrees, that is automatically telling you that the line segment is actually a negative line segment. So it's going to give you a negative gradient. Does that make sense?
Yes, thank you, ma'am.
No worries, perfect. So now we move on to distance. Distance is one of the most important things in analytical geometry because distance tells us a lot of things. I can ask you a lot of questions around distance. I mean, question around distance is not always going to be calculate the distance between this. I could tell you to prove something, and the only way to prove it could be distance. And I'm going to show you questions like that. So now, distance between 2 points is something that you should be able to calculate. We say that distance between 2 points can be calculated using any of these two equations. Really, it's all up to you. They are all the same, just that this one goes straight to the answer, the red one. So whichever one that you like, you can use, and whichever one that you understand, you can use. That is perfect. Again, the distance between 2 points, it's just the difference between the x values squared plus the difference between the y values squared. That is going to give you the distance squared. Then you can square root on both sides to figure out what is the distance. Or if you are using this equation itself, you can basically say the distance is equals to the square root of, you find the difference between the two x values, you square that. The difference between the two y values, you square that, and that's it. This one, again, I would prefer if you keep if you be systematic with it again. What is being systematic in this case? Look at the x2 minus x1, y2 minus y1. Keep it in mind that whichever point that you started with, you must also start with the x values, with the y values. Don't swap things around. Although in this case we can sort of like give a leeway because of the squared, the sign will not make any difference. But I would like you to be systematic about it also. Then on the side, I was just making notes on interesting stuff. Um, the distance formula will still apply when you have a vertical line or a horizontal line, but usually it's nice when you see a vertical line and a horizontal line, understanding that it's much more easier to calculate the distance between the 2 points in such a line segment. Because for an example, if you look at this line segment, it's a vertical line segment, meaning that the x value is not changing, as I had already told you. The x value is the same because this line is literally sitting on the same x value. What you can see as changing, though, is the y values, right? The y values are changing. So basically, to find the distance between these 2 points, it's basically you taking the top y value and subtracting the bottom y value. You take this y value here, you subtract this y value here, then you automatically have the distance between the 2 points. You can substitute these 2 points in the distance formula. It's still going to give the same answer, but if you just remember that in your exam, just take the top y value minus the bottom y value, and then you're going to get the answer. Only and only if it's vertical distance. And then that's what I wrote here. So if you're working with vertical distance, what is vertical distance? It's basically distance between 2 points such that they form a vertical line. That's what it is. Vertical distance, you take the top y value, you subtract the bottom y value, and then that is going to give you the distance between those 2 points. I think also, yes, vertical distance is important for your functions. I know when you do functions, there are those sections where they say determine the minimum distance between this function and that function at x is equal to this. So you need to just understand that vertical distance is the top y value subtract the bottom y value, and then you're going to get that answer. So it's also still applicable within analytical geometry. I can give you 2 line segments and say determine the vertical distance between the 2 line segments at that x value. So just keep that in mind. Horizontal distance, again, nothing much. It's a horizontal line. You're calculating the distance between 2 points that are on a horizontal line. How do you know that it's a horizontal line? You can physically see it with your eyes, or you can look at the y values. The y values are not changing because we did that with a horizontal line. What is changing is the x values, but the y values are remaining the same. So now in this case, we are saying the y values are the same, so we have to subtract the x values. The x value on the right, you subtract the x value on the left. So that's how you calculate horizontal distance. But again, if it happens that you forget, you can still use the distance formula. If it happens that you forget the distance formula, just think about the fact that I'm looking at the 2 points, right? If the x values are the same, I can't subtract those because I'm going to get 0, and there's no way the distance is 0. So I have to subtract the values that are different, which are going to be the y values in the first case with vertical distance. You just take the bigger one, subtract the smaller one, and that's technically it. Yeah. And then that's it with distance. Again, it's a very big, it's a very big and important part of analytical geometry. You should be able to calculate distance because again, when you do grade 12 analytical geometry, you will see someone says I'm breaking. Are you guys still able to hear me?
Yes, ma'am.
Yes, ma'am.
So I was saying that with your grade 12 analytical geometry, you will see you will have questions around 2 circles or a circle and a point that will require you to calculate distance in order to be able to prove certain things. So distance is very important, guys. Don't undermine it. Very important. And the second last thing to remind you is the midpoint, right? How do we calculate the midpoint of a line segment? So what is the midpoint? It's basically the point that is halfway between 2 points. That's what the midpoint is. So if I have 2 points, A and B, and I want to calculate the midpoint of the line segment AB, I just have to add the 2 x values, the x value of A and the x value of B, then divide that by 2, add the 2 y values, divide by 2, and that should give me the x value and the y value of the midpoints. So if you want to find the x value of the midpoint, you add the 2 x values of the 2 points, like that at the extremes of the line segment, divide by 2. For the y midpoint, which is basically the y value of the midpoint, you take the 2 y values, you divide them by 2, and then you're going to get the y value of the midpoint. I wrote these 2 equations because it's much easier to calculate the coordinates of the midpoint using this, because we know that you can just say x value of A plus x value of B divided by 2 to get to the answer, and etc. I wrote these equations to remind you that sometimes the examiner will give you the midpoint and expect you to work out one of the x values or one of the y values. So if I give you the x and y midpoint, you can use these 2 equations to calculate the coordinates of F. For example, if I say to you, calculate the coordinates of A, you can calculate XA using that equation. You can calculate YA using this equation, and then you will therefore have the coordinates of A. XA is to YA. Similarly, if I give you the coordinates of the midpoint, which is XM and YM, and I give you the coordinates of A, I would expect you to calculate the coordinates of B because you have these two equations. And in grade 11, this was like 6 marks-ish thing. In grade 12, yeah, you could still get the same number of marks. Just remember this. There's a hand. Yes, I'm listening.
Ma'am, I can't see your screen. I tried exiting and it's not working.
Okay, let's try and remove and then put it back and see if the problem still persists. Right, let me share again. Right, can you see my screen now?
No.
You still can't?
Yes, ma'am.
Oh. Now I know what the problem is. Right. Try one last time, and if the problem persists, then I don't know what is happening. Okay, I think she says she can see. That's good. Let me just go back to yes.
Are you showing something on the screen?
No, I'm showing now.
Okay.
Now you're worried that you were the one who's not seeing. I'm just gonna present now. Right. Yes, now there is something on the screen. Right. So as I was saying, these two equations are very important because they sort of like remind you that this is not the only thing that we're working with. It could be a matter of I give you the midpoint, you should give me something else. So just keep that in mind. And then the last thing before we try to look at a few equations in grade 11 is understanding how to determine an equation, right? We went a whole lot of we had a whole lot of explanations around gradients. So you should be able to determine the gradient of the line. That's the first step. When you want to determine the equation of a straight line, that we know very well that it's in the form y is equal to mx plus c. The first thing that you should be able to do is to determine the gradient of the line. Once you have the gradient of the line, you substitute that gradient into the equation y is equal to mx plus c. So in this case, I had made an example and said, let's say I have the gradient 2. And then now I would have y is equal to 2x plus c. Then now, how am I going to calculate the value of c? Value of c, as I said, it's the same thing as the y-intercept. So if they've given you the y-intercept, then you can substitute it right there. But if they haven't, you just need to find a point, any point on the line. You substitute it, and then you solve for c like that. And then you have the equation, y is equal to 2x plus 1. Someone was saying we can speak about the midpoint thing again. Yes. So I was saying for you to calculate the midpoint of a line segment, what you need to do is just you take the two values. For example, if I have this as my line, for me to calculate the midpoint coordinates, I need to take the x value of A plus the x value of B and divide that by 2. That will give me the x value of the midpoint. If I want to calculate the y value of the midpoint, I'm going to count the y coordinate, of the midpoint. I'm just going to take the y value of A, or the y coordinate of A, plus the y coordinate of B, and divide it by 2. Divide that sum by 2. And that should give me the y value of the midpoint. Then I said, remember that it's not all the time where the examiner will say, calculate the midpoint. In some instances, the examiner will give you the midpoint and expect you to give them something else. So the examiner could give you the midpoint and expect you to calculate the coordinates of what the hell? I'm Can you guys still see my screen? Right. So as I was saying, you need to understand these two equations for the purposes of, if I give you the midpoints, you should be able to give me something else. But again, you're going to see that with questions. Right, I hope that settles everything. Before I show you questions and deal with questions, I want to remind you something very important. Guys, this is analytical geometry. We do a lot of construction. I'm going to write this in capital letters so that you can put it in your brains. So this is analytical geometry. We do a lot of construction. We construct a lot. So an examiner can tell you about a circle, but the circle is not there. You need to construct the circle. They could tell you about a line segment, but the line segment is not there. You need to construct the line segment. Especially when it comes to inclination. We construct a lot to get those inclinations. So it's very important to... Right, someone is saying I'm moving too fast. I'm going to try to slow down. I'm sorry. I know I can get carried away. I was saying, just to remind you before we start doing questions, that in analytical geometry, we do a lot of construction. So they're going to tell you a lot about things that are not on the sketch, and you should put them on the sketch so that it makes sense to you. You will realize that for paper 2, you have a specific an answer book that is given to you. So whatever that you do on that diagram, your teacher is going to be able to see it and give you marks according to what your diagram says or what your drawing says. So it's very important to remember that if they say to you line segment, whatever, but you're not seeing it, it means that you should be drawing it. It's supposed to be drawn. You're supposed to put it there on the sketch. So if you forget everything about today's session, just remember that in analytical geometry, we do a lot of construction. We construct a lot. Unlike Euclidean. In Euclidean, no one is going to expect you to construct in a writer's question, whatever, and unless it's a proof. And then number 2 is to remind you that you need to understand properties of quadrilaterals and triangles, because they are a big part of your grade 11 analytical geometry. Properties of quadrilaterals and triangles. You need to understand. If I say to you ABCD is a kite, you need to understand the properties of a kite. If I say to you ABCD is a parallelogram, you need to understand the properties of a parallelogram, because me saying to you ABCD is a parallelogram, I've already given you so much information about ABCD that can help you calculate stuff. And you're going to see that in a while. So I am going to send you these properties on the group, and I'm going to expect you to know them as much as your examiner is going to expect you to know them for the exam, for that section, especially for grade 11 Euclidean analytical geometry. Quadrilaterals are a big part of that section, because they can tell you this is a quadrilateral, this, then that should give you ideas around what should be happening. So construction, keep that in mind. Properties of quadrilaterals and triangles, you need to remember them. Know the different types of triangles. If I say to you ABC is an equilateral triangle, already that should tell you something. If I say to you ABCD is a scalene or an isosceles triangle, that should also tell you something about ABC. So it's for your own good, and it's also for the completion of the questions that you're going to get for analytical geometry grade 11. So just remind me after the session to send you these properties so that you can remind yourself, what do I mean by such a quadrilateral? What do I mean by such a triangle? Does that make sense?
Yes.
Perfect. Right. There is my book. Not my book, but yeah, workbook-ish. Okay, this is not ending. Let's see. Okay, no, that's a bad one. Let's find another question to use. There's a better one. Yeah, I think this was a better one. Right. Now let's look at this question, because I feel like it ties up everything that I was speaking about and just put it into perspective. So you might have something like this for your question 3, where they say to you ABCD is a quadrilateral with vertices A, B, C, and D. You are given points. Those vertices are basically corners. The examiner is telling you about corners, right? So the examiner says you have ABCD as a quadrilateral, meaning it's a shape that has 4 sides. And then they're giving you these coordinates. And then the first question that they ask you is to determine the coordinates of M, the midpoint of AC. How do we do that? Anyone?
You use the gradient formula.
Right. So I'm trying to calculate the coordinates of the midpoint of AC. You can see on the diagram that we do not have AC. I just constructed AC. That's what I meant when I said we do a lot of construction in analytical geometry. So you're going to have to construct AC and then think to yourself that you're calculating the midpoint. So as I had told you, we calculate midpoint again by saying we take the 2x values. Which 2x values am I taking, or 2x coordinates?
-3 plus
-3 and 2.
Right, divide by 2, right? And then y values, it's going to be 0 plus -1.
And -1.
And then the midpoint will be -1/2 is to -1/2, if I'm not mistaken, if my brain works. So now we can tell from the fact that we have a negative x value and a negative y value. So this point of ours is somewhere here. This is our point M. -1/2 is to -1/2. It's both on the negative y-axis and also on the negative x-axis. I know that because the coordinates of M are -1/2 and -1/2. Then now the question says, show that AC and BD bisect each other. This is a very important statement. First things first, you need to remind yourself, what does it mean to bisect, right? So bisect basically means to cut in half, right? To cut in half. So the question now says to you, show that the line AC and BD bisect each other. Just to give you perspective before I show you the calculation and stuff. If I have this line like this and this line like that, and I tell you that this, right, this is equal to this, and this is equal to that. This first things first, let's look at this. So if this part is equal to this part, what is this part for the purple line? I'm going to repeat my question. Perfect. That's the midpoint, right? So if this point right here is cutting the 2 parts into halves, this should be the midpoint, right? But can you see that for the other line, it's also this part is equal to that other part? That automatically tells you what? That this part is also, again, the midpoint of the other line. So the conclusion now from this is that for 2 lines to cut each other in half, what must happen? They must have the same midpoint. Because if they have the same midpoint, then that tells us that no, actually, these 2 lines, they are bisecting each other. Because that is the conclusion that we're making from that. We are saying if we were given that the 2 lines are bisecting each other, what we are observing is that for 2 lines to cut each other in half, those 2 lines must have the same midpoint, because the point where they are cutting each other is the midpoint to both of them. So one is cutting each other in half, that is at the midpoint, and the other one is going to cut the other one in half at the midpoint. So these 2 points are sharing a midpoint. So what is it that we are supposed to be proving in that question when they say to us, prove that AC and BD bisect each other? The question just says to us, prove that if I draw the line BD like this, let me use a this. If I draw the line BD like that, right, I am going to get the same midpoint. I'm going to get the same M. Like what I'm going to get is the coordinates of M. So again, that's another calculation, right? Let me just make this big because now it's ruining my analogy. But now let's do the calculation to prove that. So how am I going to calculate the midpoint of BD? Anyone?
Till the midpoint of BD.
Midpoint of BD, yes, it's going to be
0 plus
Negative one
negative
plus
1 all
two.
over 2.
yes, and
2 plus negative 3 all over 2.
perfect. And now, if you do the math really well, this is going to be negative 1 over 2 is to negative 1 over 2, which is the same answer that we got for the first one. And that automatically shows us that, oh, these 2 points have the same, these 2 lines have the same midpoint. So having the same midpoint basically tells us that they bisect each other. It's just another way that the examiner uses to say, determine the midpoint of BD, right? So instead of telling you to calculate the midpoint of BD, they said, would you understand what I mean when I say show that AC and BD bisect each other? That's you basically calculating the midpoint. And that's it. So we've answered the question. And then now the examiner says to us, prove that ADC, you can see it right here. This is our ADC right here. They're saying it must be proven to be 90. Yes?
Can you please repeat 1.2 from where you started constructing line AC and line BD?
Right. So AC and BD bisecting each other, that can only and only happen if they share the same midpoint. So we just made a construction to show the line BD and the line AC. And we are saying for you to prove that these 2 lines bisect each other, for them to bisect each other, they must share the same midpoint. So if we can prove that they share the same midpoint, then we would have proven already that they bisect each other. So what we did was to calculate the midpoint of BD to check and confirm that does it match the midpoint of AC? And it does, because the midpoint of AC that we calculated in 1.1 was negative half, is to negative half. Similarly with the one for BD. So the fact that they share the same midpoint is proof enough that they bisect each other. Does that make sense?
Yes, ma'am.
Right. Someone has raised their hand. Yes.
Hi, ma'am. I wanted to ask, with question 1.2, aren't you supposed to end off with some sort of conclusion to say that the midpoint of AC is equal to the midpoint of BD?
You can. So, for example, show, every time you show, when they say show something, you're basically calculating something. So the biggest interest that we have is in the calculation, because the calculation is proof enough, right? So it's a good thing that you're thinking like that, because it's very important to make conclusions. So yes, you can make the conclusion and say the midpoint of AB is the same thing as the midpoint of AC. Therefore, they bisect each other. That's very good.
Thank you, ma'am.
Right? Perfect. So after doing the calculation, as you said, you can say the midpoint of AC is equals to or the same as the midpoint of BD, therefore they bisect each other. That also shows the examiner that you know your work. You know why you had to calculate the midpoint. Very good question, by the way. And then now, the third question says prove that ADC is 90 degrees. That's where we're at. So there are multiple ways in which you can prove that angle is 90 degrees. One of them is the angle 90 degrees automatically tells us that this line is perpendicular to this line. Does that make sense? When there's an angle of 90 degrees between 2 line segments, this line segment here and that line segment there, if there's an angle of 90 degrees between those 2 lines, then that tells us that, oh, these two line segments are perpendicular to each other. So how can you prove that AD and DC are perpendicular?
By multiplying
Use
the
the
gradient.
Perfect, right? We have all the points. We have A, we have D, we have C. So we can basically do the calculation using points. So we can calculate the gradient of AD, calculate the gradient of DC, multiply the gradients, and see if we get a negative 1. If we get a negative 1, that means that AD is perpendicular to DC. Then we can start saying, okay, therefore that is 90 degrees because those two lines are perpendicular to each other. Now, let's do that. What is the gradient of AD?
2/3.
2/3.
Right, so it's going to be the gradient of AD is going to be equal to change in y, which is going to be 2 minus negative 3, 2 minus 0, and then divide by 0 minus negative 3, which is going to be 2 over 3 as we said. So it's a convincing answer because it's a positive answer, and the line segment AD is an increasing function. Then now the gradient of DC, what is it going to be? Substitution?
Negative 3/2.
So let's substitute the y values. So it's going to be 2 minus negative 1 over 0 minus 2, which is going to give us negative 3 over 2, right? And now, if we take the gradient of AD and multiply it by the gradient of DC, we are going to have 2 over 3 multiplied by negative 3 over 2, where this goes, that goes, and then you're going to have negative 1. And then you can conclude and say, therefore, AD is perpendicular to DC. Therefore, ADC is 90 degrees. That's proof enough, right? Again, if we can prove that AD and DC are perpendicular, we can prove that there's a 90-degree angle there. How do we do that? We find the gradient of AD because we can. We find the gradient of DC because we can. We therefore multiply the two gradients. And then if they give us a negative 1, like they did, then we can be sure that, okay, that is perpendicular to that. AD is perpendicular to DC. Therefore, there's a 90-degree angle. But there's another method we could have chosen. There's another route that we could have taken instead of the multiplying the gradients, which is sort of like a longer route. But assume that it probably was the only way to get to the answer. I'm just making an example. So can you see that from the sketch, if I can calculate theta and calculate beta, I can use some angles of a triangle to find ADC. Can you see that? I'm going to repeat this. Can you see?
Yes.
Can you see that if I can find the size of theta and find the size of beta, I can use some angles of a triangle to calculate ADC. Let's call this angle alpha, like that. So I can use that method. Let's see if it works. Now, we know we've calculated the gradients for the two line segments. I'm happy. So we know, let me just remove this because I'm trying to run away from opening a whole new page. So we know very well that tan theta is equal to the gradient of which line segment? Which gradient is equal to theta?
DC.
CD, right? Yes, because we can see that CD is the line segment that is making the angle theta. Perfect. So we say tan theta is equal to, we have calculated the gradient of CD right here, and we've calculated it as negative 3 over 2. So we want to say that's going to be equal to negative 3 over 2. Now, we say theta is equal to upton negative 3 over 2. And then what do you get when you punch your calculator?
Negative 56,309. Should I round it off?
309 something something. Okay, that's cool. But remember, I told you that angles of inclination are positive angles, right? Do you remember when I said that? When I said the angle of inclination
Yes.
always has to be positive. So if you get a negative angle of inclination, you must add 180 to make it positive, right? Number two, the negative angle is the angle alpha. Because remember, I said if we're looking at the straight line DC like this is a positive angle, this is a negative angle. How do I know that? Theta is made in an anti-clockwise direction, hence it's the positive angle. Alpha is a negative angle because it's made in a clockwise direction. So one gradient can give me two angles. I just need to pay careful attention. Am I getting a positive angle? If I'm getting a positive angle, then I'm going to therefore say that is my theta. In this case, we got a negative angle. That is telling me that, okay, that is alpha, but I can get theta by adding 180 because alpha and theta are angles on a straight line. That's why we add the 180 to get the other one, because these two angles, alpha and theta, one is a positive angle, one is the negative angle. We add 180 because they're angles on a straight line, and then that's it. So that's how we get one over the other. So just keep in mind that when you do this calculation, you must always get a positive angle at the end of the day. If you get a negative angle, you must add 180 to make it positive. But also keep in mind that when you're looking at the line segment, theta is a positive angle, but the negative angle is alpha, which is opposite theta, which is just right next to theta, made by the same line segment. I'm seeing two hands. Yes, people, we can speak. Question? Right. So I'm seeing a question on the chat.
I wanted to ask something.
Mm-hmm.
Yeah, I wanted to ask something, but you haven't explained, so I'll wait to re-explain. Then if I don't understand, I'll ask.
Okay, no worries. So just to re-explain what I was saying, I said when we did the calculation here, we got a negative answer, right? And I said to you, you can never ever have an angle of inclination that is a negative. An angle of inclination is always going to be a positive number. If you get a negative number, that tells you that you are getting the other angle that is opposite to the angle of inclination. In this case, the angle of inclination is theta. Because you are not getting a positive number, it means that we are getting alpha. Why? Because I said to you, an angle of inclination is positive because it's formed in an anti-clockwise direction from the positive x-axis to the line segment itself. That's a positive angle, right? But the angle theta in this case, it's formed by the same line segment, but in a clockwise direction. And angles that are formed in a clockwise direction are negative angles, like this. So that is why I said when we did the substitution here and found a negative angle, we know very well that the negative angle is alpha because it's a negative angle. It's an angle that is formed in a clockwise direction. So for us to calculate the angle theta, we need to add 180. And why are we adding the 180? We are adding 180 because alpha and theta are angles on a straight line. And we know that adding them all together, we're supposed to be getting 180. So that's why we're just saying plus 180. It's like we're just saying 180 minus the angle alpha. And that is going to give us theta. And that's what we're doing. Yes, I'm seeing a hand.
Ma'am, I wanted to ask. So when we add the 180, we're calculating for theta, but then didn't we want ADC? And why would we need theta to get ADC?
So we're not there as yet. We're not calculating it. We're not at the step of calculating ADC. We are firstly figuring out the angles that will help us calculate the angle ADC.
Oh, okay. Thank you, ma'am.
No worries. Remember I said we need to find theta or alpha first, then we find beta, then we can find ADC. So that's our step right now. Yes, Mbali, I'm seeing a hand.
Ma'am,
Yes.
I don't understand the negative angle and the positive angle.
Right. So a negative angle is an angle formed in a clockwise direction from the x-axis. So clockwise direction in the direction of the clock, in the way the clock moves. Anti-clockwise direction opposite to the movement of the clock. So you know that your watch moves like this, right? Exactly. So a negative angle is an angle that we are forming in the clockwise direction, like alpha. Alpha is an angle between the x-axis and the line segment itself in a clockwise direction. That is called a negative angle. When you look at theta, I'm not forming theta like this, right? Theta is formed in the other direction. So it's formed like that. So that makes theta an angle that is formed in an anti-clockwise direction, anti-clockwise, which makes it a positive angle. Again, for you to remember positive and negative angles, think of the Cartesian plane. In the Cartesian plane, we have 0, and this is 90, and this is 180. So you can see that in the Cartesian plane, we go like this. We go in an anti-clockwise direction to form positive angles. The moment you start going in this direction, this is the negative direction, right? So we are saying if you're doing a calculation like we did right here, and you find a negative angle, that automatically tells you that this is not the theta that you're looking for, because I keep on saying to you guys, an angle of inclination can never be negative. An angle of inclination can never be negative because by definition, an angle of inclination is made by the positive x-axis and the line segment in an anti-clockwise direction, which means that it is always positive, because I just told you that all angles that are formed in an anti-clockwise direction, all of those angles are positive. So by definition, an angle of inclination will always be positive. So now for us to get the positive angle, we know that the negative angle is this one, the alpha. For us to get the positive angle, we add 108. And why are we adding 108? We are adding 180 because if you look at alpha and theta, these are two angles on a straight line, right? And we know that angles on a straight line are supposed to be giving us 108 when we add them together. So what we do is to say, if I get a negative angle, because I know that the angle of inclination has to be positive, I'm going to add 180 all the time. I get a negative angle. But if when I did the calculation, I got a positive angle, you don't add 180 because it's that angle of inclination. The goal is to have a positive angle when you're doing this calculation. That's all I'm saying. Because all angles of inclination are positive. So the goal is to make the angle positive. How do I make the angle positive? I add 180. Is that making sense?
Yes, ma'am. Thank you.
No worries. What do we get when we add that?
123.6.
Perfect. So now we can come back to our
123. Oh, never mind, man. It's fine.
123.
Yes, it's right, man.
All right, no worries. Thank you. So now we can come back and say, okay, now we've figured things out. So now we know that this is 123.69. And this right here, let me just erase this. This alpha right here is, what was it again? 56.31 degrees, right? So this is our alpha, this is our theta. And then again, you can just, on your write-up, you can write that alpha is equal to 56.31 degrees. And then the reason is that angles on a straight line, right? So we have alpha. Then now we need to calculate beta. Now, is beta made by the same angle of inclination as alpha and theta? Oh, as theta. Sorry. Is beta made by the same straight line as theta? That's my question.
No.
No, it's a different straight line, right? So now it's AD instead of CD, right? So that automatically tells you that you can't use the same gradient to calculate beta. You need to use a different gradient. So you need to use the gradient of AD to calculate beta. And if we had already calculated the gradient of AD, which was 2 over 3, right there at the top, if you can have a look. So we can just say right here that tan beta, don't forget, it's not theta anymore because of the fact that we're calculating beta. So just make use of the angles like that. So tan beta in this case is going to be equal to the gradient of AD, which is 2 over 3. So we are saying tan beta is equal to 2 over 3, which is the gradient of AD. When you punch your calculator and say at tan 2 over 3, what do you get?
33,69.
33,69.
Right. Do I have to add 180?
No.
No, because
No.
it's a positive angle, right? I would have added only if it was a negative angle. So it means that that is perfectly fine. So that is technically it. Before I forget, let's just come back here. It's also very crucial that once you've figured out that this is a negative angle and you add 180, just also go back and add 180 here, because this is now going to be a little bit not making sense to the examiner if you're only adding 180 towards the end of the step. So just start adding 180 there. But again, how are you going to know that you need to add 180? Just do this, right? Let me just show you. Write it like this initially. Then when you punch it on your calculator and find negative something something, then just add 180 like this. And then continue your calculation. But I don't think they would penalize you, just again for formality and to make sure that the maths is consistent and true. Yes, someone has raised their hand. You can speak.
Oh, my question is, like, if we decided to have U beta loyal, like, should we indicate in the answer that you constructed beta or what?
Oh, yes, that's a very good question. So it's very, again, I told you that in your paper 2, you are given an answer book. So if you have indicated in your answer book that beta is that angle, then you are fine. But if you don't indicate, then the examiner doesn't know what is beta. Because when they are marking your script, they are also looking at your diagram. So they're also looking at what you're doing. If you want to be safest, but again, in this case, you can't really be the safest because we don't have a name for this point. So I can't even say DA something, that angle. So you really need to name it. So you must put it on your diagram. Does that make sense? Or you can say inclination of AD. That also works. If you say tan inclination of AD. But like it would be nice if you just label it. If you label it on a diagram, the examiner has to mark it like that. Do you get my point? Because that's why you also get the sketch on your answer book so that you can draw on the sketch and show them that this is that. So we have beta, we have alpha, we have theta. Now we can calculate the angle ATC. So using some angles of a triangle, how can I? There are two ways. You can use some angles of a triangle, or we can use exterior angle of a triangle. That also works. So if you're using some angles of a triangle, we know that, let me try and do it like here. We know that ADC, which is what we're trying to calculate, plus beta, which is 33.69, plus alpha, which is 56.31, that must give us 118, and that is some angles of a triangle, right? Then I am hopeful that when you do this calculation, this is going to be plus 90 is equals to 180 degrees, and then ADC is equals to 90. That's another way of showing that that angle right there is 90 degrees. It just depends on which one came first. Is it the gradient, multiplying the gradients, or is it this? I'm seeing two hands. Yes, guys, we can speak.
Oh, sorry, ma'am, I forgot to. Yeah, where's this man?
No worries. Bali?
Ma'am, just for clarity, can I please ask the 180 to be added even though the angle is not in the straight line?
You add the 180 if you punch your calculator and you get a negative angle.
Okay, ma'am. Thank
That's
you.
when you add 180. And please, again, the other thing that is important to note, guys, I did not remove any signs. You substitute the gradient as it is because that changes everything. If you now substitute a positive gradient, if it was negative, that now changes everything. So please stick to one thing. If you substitute the gradient as it is, like me, substitute the gradient as negative so that you can add the 180 like this. Please, I am begging you, please. So substitute the gradient as it is. Don't try to change it. Don't change it. Don't change the sign. Substitute it as it is so that everything that I'm speaking stays true. Because if you change the sign now, it requires me to explain other things, which changes everything that I've spoken. So substitute the gradient as it is. If you get a negative, add 180. If you get a positive, voila, perfect. You are there. All the time you're keeping in mind that what you're fighting for is a positive angle of inclination. So if you get it, perfect. If you get a negative, add 180 so that you can get it. And that's it. So yes, this was the other way of showing that this is 90 degrees. Are we all clear? That is making sense. Right.
Yes,
Up.
ma'am.
Okay. So it really here it was it depended on which idea came first to your mind into your mind, because the examiner did not necessarily restrict you from using any other method. So now the fourth question says prove that or show that ABCD is a square. And this is where I say you need to understand the properties of quadrilaterals, right? So understanding the properties of quadrilaterals is again understanding what makes a square, right? What makes a square? We know that for a square, all the sides are supposed to be equal. If that is a square, all the sides are supposed to be the same. That's what makes a square a square. Yes, we know that the opposite sides are supposed to be parallel, whatever. We know that. But other quadrilaterals also have that. Like your what is that? Your rhombus, your whatever. So what makes a square is that one, all the sides around it are equal, right? AB is the same as BC, is the same as CD, is the same as whatever. And the other thing we know that by proving that one of the interior angles is 90 degrees, already we are halfway through proving that this is a square. Because the difference between a square and a rhombus is the 90-degree angle. So because we already have proven that we have a 90-degree angle here, we have some sort of starting point. But the next thing that we need to prove is to show that all the sides of the square are equal. Is to show that this side is equal to this side, is equal to that side, which is equal to that side. How do we show that? How do we show that all the sides are the same?
Distance formula.
Calculations.
Perfect. Distance
Okay.
formula. Yes, is the equation. Right. So we're going to calculate the distance around the different points. I had calculated it, I'm sure. Okay, I don't know where my distance went. But yeah, so you're going to calculate the distance around those points, and you're going to find out that the distance is the same around all those points. So yeah, that is technically it. So to work out this question, one, again, I think I mentioned this. Okay, it was not with you guys. It's important that you understand quadrilaterals or the properties, because if you have at least two of the properties, you can conclude that a certain quadrilateral is a square or a rectangle or whatever. So in this case, already we know that one, the interior angle, in that we have 90 degrees. One of the interior angle is 90 degrees. The moment you have proven or shown that one of the interior angles is 90 degrees, and then you've shown that all sides are equal, you are fine. You don't even need to prove for us that the opposite sides are parallel or whatever. Because again, as I told you, what makes a square really is that all the sides are equal and one of the angles inside is 90 degrees. one interior angle is 90 degrees, because as long as one is 90, all of the others are going to be 90 also. So this 6 marks, how you're going to get it is 1, by calculating the distance between AB, the distance between BC, the distance between CD, and the distance between AD. And I'm sure you're going to get the same answer. And then you can therefore say all the sides are equal. One of the interior angles is 90 degrees. Therefore, ABCD is a square. Right. Is there a question around that? Is anyone not understanding how they're going to show or prove that that is a square? Right. Okay, cool. Now they're saying to determine the size of theta, the angle of inclination DC, correct to 1 decimal place. Clearly, this examiner was not as smart, because if you ask this question right here, and I'd already calculated this, you're sort of like a forced to give it a mark. But either way, you can redo the calculation of calculating the size of theta, of which you had already calculated. So we know that theta is 123.69 degrees. We had already done the calculation. So you can do it again. It doesn't mean that you were wrong. It doesn't mean that the method that you did is wrong. It's mathematically correct. And especially since the examiner did not direct you towards a specific method. So that's it. And then the last question, are you guys fine with question 1.5? Are you getting it? Are you with me? Okay. The last question is a very interesting one, because it's a grade 11 question, but also a very important part of grade 12, because that's the first thing that you're going to do with circles. So the question says to you, does C lie inside, outside? In grade 12, they're going to also say, or on the circumference of the circle. And you must justify your answer. That circle, you are told that it has a radius of 2. So again, we'll speak more about this when we do Analytical Geometry Grade 12 next week. Right. So so they're saying to you, have a circle. The circle is not on the diagram, as I told you. There's too much construction that we do in this section. So you have a circle. The circle has a center 0 is to 0. So the center of the circle is at the origin, because we know that the point 0 is to 0 is the origin. Right? We know that that is the origin. So let's go and look at where the circle would be at. So the circle is somewhere here. Right. Yeah, we're not sure whether the circle is here or the circle is something like this. Because remember that what we're trying to prove as to whether this point C, is it inside the circle? It would be inside the circle if that circle is the green circle, or it's outside the circle. It would be outside the circle if our circle is the pink circle, right? So now, how are we going to show or prove? Okay, remember there's another important detail that they told us. They told us that the radius of the circle is 2 units, right? So think about this properly. If I have, remember this is my center. They said my center is at 0 is to 0. If that is my center right there, and I have a radius like this, which is 2, or my radius could be something like this, right here and right there, which is supposed to be 2. So can you see that if I can calculate the distance between point C and the center of the circle, like assuming that, yes, if I calculate the distance between point C and the center of the circle and compare it with the radius, do you agree with me that if the radius of the circle is smaller than the distance between the origin and C, then C must be outside the circle? Whereas if the radius of the circle is much bigger than the distance between the center and point C, then point C must be inside. Let me show you a sketch, because I can see that I'm speaking. Yes, I'm trying to show you a sketch, because that one is too messy. That's how you can't see it. I am saying to you, I have a circle like this, right? I have the origin, which is at 0. Let me just try to make the pen a little bit right. I have this is 0 is to 0. So this is my origin. And then there's a point C. The question that they are asking me is that, is point C inside the circle like this, or is point C outside the circle like this? Then I'm saying to you, how are we going to know? Picture this. This right here is the radius of the circle. Do you agree with me if I say that that is the radius? Do you agree with me? Okay.
Yes.
So they told us that the radius is 2 units, right? So what are you noticing between the radius and the distance between the origin and C if C is outside? Is the distance between the origin and C greater or less than the radius?
It's greater.
It's greater, right? You can see with your naked eye that if the point is outside, there's going to be a bigger distance between the origin and point C compared to the distance, which is the radius of the circle. But see it from another angle, right? Let's look at the one when it's inside right now. Can you see that again, we still maintain that this is our radius. We're just drawing it from another angle. This is my radius right here. The radius is said to be 2 units, like this. Can you see that the distance between the center and C? Let me just do this. Why is it not straightening up? Right. Yeah. Right. Can you see that the distance between the center and C? Okay, let me not tell you the answer. How does the distance between C and the origin compare to the radius? Is it much bigger or smaller?
Smaller.
Smaller, right? So now we are saying from this observation, we know that since they've told us that the radius is 2 units, if I calculate the distance between the origin and C and I find that it's a bigger number, does that mean that C is inside or outside? I'm repeating this. If I calculate the distance between, if I calculate the distance
outside, ma'am?
if I calculate the distance between the origin and C, and I find that that distance is bigger than the radius, is C inside or outside?
Outside.
If I calculate the distance between the origin and C, and I find that that distance is smaller than the radius, is C inside or outside the circle?
Inside.
And then that's how you're going to basically solve the question. You just need to calculate the distance between the origin and C and compare it with the radius of 2. And let's do that, right? So how do I calculate distance? Again, I have my origin, which is 0 is to 0. What is my point C? My point C there is 2 is to negative 1, right? So how am I going to calculate the distance between these 2 points? Distance is equal to the square root of x2, which is going to be 2, minus x1, which is 0 squared, plus y2, which is negative 1, minus y1, which is 0 squared. And your calculator, what do you get?
Root 5.
You're getting what? Root 5 units. And then if you convert it to decimal, what do you get?
2,23.
2.23.
Yes.
So now the question is, when you compare the distance and the radius, is it greater than or less than?
Greater than.
Therefore, what is the conclusion?
It's outside the circle.
C lies outside the circle. And that's it. I like these questions because you can do a sketch like mine to figure out the answer. I'm going to show you again when you get to analytical. Very important concept to understand. I'm just going to ask you out of interest this one because we're running out of time, about 10 minutes. How would I know if a point is on the circumference of the circle? Like, how would I know that C is actually here? What if C was here? How would I know?
The distance is equal to the radius.
It'll be equal to the radius.
Very good. So you can see that if I draw the line segment here, that would be the radius, right? So if I compare the distance between the origin and, not the origin, the distance between the center and the circumference. Sorry, if I compare the distance between the center and point C, and then compare the radius, I'm going to get the same thing. Like both of them will be the same thing. And that will tell you that the point C is at the circumference of the circle. So we have three conditions. We have a condition 1 where the point is outside the circumference of outside the circle, a point where it's on the circumference of the circle, and the point where it's inside the circle. How do we know this? We are saying if it's outside the circle, the distance is greater than the radius. We're saying that if it's on the circumference of the circle, the distance is equal to the radius. If it's inside the circle, the distance is smaller than the radius. And again, you see how I've written my conclusion? I also would like it to appear like that on your script. Distance is greater than the radius, therefore C lies inside, or outside the circle in this case. And then that's it. Before you leave, we have like about 10 minutes-ish. I just want to show you, not this. I haven't told you this yet. Where is my question? Right. Let's try. We're not going to work through this one. I'm going to work through it. But I'm just trying to highlight something. There's a question that is missing in my set of questions, and I'm not happy. Where is it? I'm supposed to be the first one. Okay, that's cool. Right. So let's just have a look at this. Again, just to refresh your memory as to what they're going to be asking you. Yes, I'm seeing a hand. You can ask. Hi, Ona. Do you have a question?
My answer did get my question did get answered. That's okay.
Okay, no worries. Thank you. I'm not gonna be doing this thoroughly with you. I'm just trying to prove some point. Right. So ABC is a triangle with the vertices ABC. They're telling you that P is a positive number. That makes sense. That for P to be a positive number because it's on the positive x-axis on a Cartesian plane, and they're saying to you AB makes an angle of 45 degrees with the positive x-axis. Is AB the angle of, is 45 degrees the angle of inclination of AB or not?
Yes.
Yes, it is, right? Because it's in an anti-clockwise direction. Perfect. We're told that AC is the root of 50 square root of 50 degrees, or root 50 units, not degrees. Oh my gosh. Right. Then the first question says to you, determine the gradient of AB. How can you determine the gradient of AB?
By manipulating the increment.
Tan 45, right? Because we have the right? Tan 45 is equal to 1. So we know that the gradient of AB is 1. Because we know that the inclination is 45. So we're going to say tan 45 and then get 1. And that's the inclination. We cannot use change in y by change in x because we don't have the value of t there. So that is sort of like preventing us from using coordinates. So the only way to get to the answer in this case is tan 45. Then the next question says to calculate the value of t, which should be easier if we know the gradient, and we know that the gradient is change in y over change in x. We have all the coordinates except for t. We can substitute that and substitute the gradient that we already know, which is 1, and then solve for t. And that should make sense. Is that making sense to you?
Yes, ma'am.
No, ma'am.
Yes, ma'am.
Right, so what I was saying was that now we do have the gradient from tan 45. We know that the gradient is 1, right? We know that change in y is going to be 3 minus 0 over changing x, which is 1 minus t. Then we can solve for t. That's what I was saying.
Oh,
Then,
yes.
now, perfect. Now they're saying to calculate p, the x-coordinate of point C. How are we going to calculate p?
Using
We
the
have
length formula.
perfect.
By
We
using
have
the
distance, right? We have distance, so we can substitute in the distance formula and solve for p, just like that. Hence, determine the midpoint of BC. So if we have the value of have the value of t and the value of p, we can calculate midpoint, right? Do you still remember how to calculate midpoint?
Yes, ma'am.
Yes, ma'am.
Perfect. Then the last question says determine the equation of the line parallel to AB passing through C. So again, construction, whether you like it or not, to make your life easier. So we have a line that is parallel to AB and this line is passing through C. So it's a line like this. It's parallel to AB. At the same time, it's passing through the point C. So how are we going to get the gradient of this line?
The gradients are equal because they are parallel.
Perfect. So if we know the gradient of AB, which is 1, we automatically have the gradient of that line. That doesn't have a name. We just know that it's passing through C. That line has the gradient of 1 also because we know that the gradient of parallel lines is the same, right? Then how are we going to determine its equation? We have the point C, so we can substitute into y is equals to mx plus c to solve for C. And then you can automatically determine the value of C, and then you're going to have the equation. And that's it. So what is the point that I'm trying to prove? From your grade 11, you should be able to calculate the gradient of a function. You should be able to use the normal gradient calculation to calculate coordinates. Because remember, the question is not always going to say calculate the gradient. Sometimes it can be using the gradient, you need to be able to calculate something else. You should be able to calculate the midpoint. You should be able to determine the equation of a line. So the word, in this case, you know that you're working with a parallel line, which makes it easier to figure out the rest. Because if you're working with a parallel line, you know that the gradients of parallel lines is the same. And therefore, yeah. Another point to be proven, look at this question. Again, I'm not going to do it thoroughly. I'm just going to be sort of like taking you through it until 10 past. The diagram below shows points P, Q, and A is the midpoint. They're telling A is the midpoint of PQ. And then they're saying to you that AB is perpendicular to PQ, and they've indicated on the diagram. And then they're saying to us, PQ is intersecting the x-axis at G. Sorry, no, AB is intersecting the x-axis at G. So again, you can see a lot of things on the diagram, but one thing that we are also seeing is that we are seeing line segments, right? Which is perfect. Now, the first question says to you, show that the gradient of PQ is negative 1 over 2. How can you do that?
By using the gradient formula, because
Using
you
the gradient
already given
formula,
the
right? Perfect.
Yes,
We
ma'am.
already have the coordinates. I have the coordinates of P, I have the coordinates of Q. So why not use the gradient formula? That's easy. So that we know that this gradient therefore becomes negative 1 over 2. Then now they say to determine the coordinates of A. How am I going to determine the coordinates of A?
It's the midpoint, ma'am. You're gonna use the midpoint formula.
Midpoint formula, right? Midpoint formula, you add the two x values, you divide by 2. You add the two y values, you divide by 2. And that's your answer, right? Determine the equation of the line AB. How are you going to do that?
The gradient of PQ and the gradient of PE is, it must give us 1, which is the gradient will give us 2.
Perfect. The first thing that you need to know, obviously, when you determine an equation is to understand the gradient of a function, right? So we don't have the coordinates of B, which means that we cannot use the gradient formula to calculate the gradient of AB. But we know that there is a relationship between this line here. I don't know if it's clear. I'm just trying to make it a little bit bigger. There's a relationship between this line here and this line here. And because they're perpendicular to each other, there's a relationship between their gradients. So since I have the gradient of PQ, automatically I have the gradient of AP. What is the gradient of AP going to be?
2 over 1.
2. Perfect, which is 2 over. Perfect, right? And then now I have the gradient of AB. How do I determine the equation then? Obviously, you're going to substitute the point. Which point do I have?
A.
Do I have exactly, because we calculated it in 4.2. You have that point, you substitute it, you solve for the value of C, and then you get the equation. Now, imagine that is for 5 marks. Guys, you need to get these marks. Then calculate the length of BQ. How are you going to calculate the length of BQ? What is the first thing that you need to do?
Distance formula.
Distance formula.
What is the first thing that you need to do before
Oh, you
that?
need to find the coordinates of B.
Oh,
Perfect. You need the coordinates of B, right? Do we have the x value of B? Yes.
Yes,
It's
it's
0.
0.
Yes,
It's
so
a, what is that? It's a y-intercept. The x value of 0 is 0. What we need to figure out is the y value. And how are we going to figure out the y value?
We have the gradient and we have the coordinates of A, which we can create a formula.
By
We
using
can
the
use the
formula
gradient.
that we got.
Yeah, there are multiple ways. We can use the gradient formula. We can use the equation that we determined here, right? So we can use that equation and say y is equals to mx plus c. Y is equals to, you substitute the x value, and then you get your answer. You get the y coordinate of B. And then now, after you have the coordinates of B, then you can calculate the length of BQ, which should be much easier. So let's assume we have the length, right? This is x units. And now the question says to you, again, show that triangle BPQ is an isosceles triangle, or show that it's isosceles. So again, it shows you that you need to really understand or remember quadrilaterals and triangles. So remember that when we're talking about an isosceles triangle, we're talking about a triangle that has 2 sides being equal, right? This is isosceles, right? So which means that you need to show that 2 of these sides are the same and they're not the same as the last one, the third one. So we have the length of BQ. That should already be giving an idea that BQ is going to be equal to something else. We have the coordinates of PQ. So we can calculate, we can calculate the length of PQ and the length of PP and then compare, right? So do you guys hear what I'm saying? Like, do you see that you can calculate the lengths? Because you have the coordinates for all of them. Right. So you can use the distance formula for this one. But then for this one, you don't really need to use the distance formula because it's vertical distance. You can just take the y value here, say minus the y value here. Then you're going to get the distance between those 2 points. So to show that it's an isosceles, 2 of these lengths must be equal or must be the same. The last one cannot be the same as the other one. That is why it's important to calculate all the 3 sides, because calculating just 2 doesn't prove anything. You need to calculate all 3 and show me that 2 of them are the same. The last one is not the same as the other ones. That is isosceles. Because if you calculate just 2 of the sides, it could happen that the third one is also the same. So that could be equilateral. So that's the point that I'm trying to make. You need to calculate or show all of them. Yes, Uyanda?
Ma'am, can you hear me?
Yes, I can hear you.
I wanted to know if we said the x coordinate of B is 0 because it was a vertical distance.
The x code. Yes, you could use that analogy. Very good. We could use that analogy that because we can see it's literally a vertical line. The point B is on the y-axis, which is a vertical line. Then its x value has to be the same as the point above it, which is 0. Or we can use the analogy that if you can have a look at the line segment AB, you can see that B is basically the y-intercept, right? What do we know about y-intercept? X is equals to
0.
Perfect.
Okay, thank you, ma'am.
No worries. So, again, that is how you're going to prove that it's an isosceles triangle. You're going to prove it's an isosceles triangle by calculating the 3 sides and showing that 2 of the sides are the same. The third one is not the same as the other side, right? then that's how you're going to prove or show that this is an isosceles triangle. The last one is saying if PBQR is a rhombus, and this is a very important statement that I'm going to make. Very important. If an examiner says P, B, Q, R, and you don't have an R on the diagram, it means that you need to construct the R on the diagram. And you're going to construct the R in the order as it appears on the letters. I don't know how to put that nicely, but this is what I mean. So the examiner says P, so P is the first one, B is the second one, Q is the third one. That means R is the fourth one. They say it forms a rhombus. So the only way to form this rhombus is if R is somewhere here, so that we form this nice rhombus looking like thing. Do you get my point? You cannot just say R is here. It's not going to make a rhombus. When you try to join these 3 points, it's not going to create a rhombus. You know that the rhombus is like a square, right? Right. So again, what is it that you're saying? The understanding of quadrilaterals is important. You need to know what is the rhombus, what makes a rhombus a rhombus. So the point that I was trying to make with this is that your quadrilateral must be formed exactly the way the letters are enlisted by the examiner. So the examiner said PBQR. So we have P. Let me just erase this, start afresh. So the other way in which you can look at it is you have P, you have B, like this, you have Q, like that. For you to enclose this thing, it means that your R must be somewhere here so that you can close this thing nicely, right? Because remember, you need to form a rhombus. That's why it's also important to know how that particular thing looks like, right? So this is going to be our P, P, Q, R, like that. So you know that R is somewhere in the first quadrant, right? So also understanding the properties of a rhombus. One of the things that I can tell you is that a rhombus is like a square. The only difference between a rhombus and a square is that the interior angle, not 90 degrees. Thank you. So this side is going to be equal to this side, which is going to be equal to this side, which is going to be equal to that side. The diagonals bisect each other. I used to love this a lot in grade whatever. I used to love saying that. Diagonals bisect each other, meaning that they cut each other into 2 equal halves. They're going to have the same midpoint, and etc., etc., etc. So understanding that will help you calculate the coordinates of R. And someone might be saying, how? Now I'm going to give you the idea. So if I know, remember that we have already calculated the coordinates of B, right? Let's just make an example. Let's say that B is 0 is to, I don't know, let's say -5 by some magic. I'm not saying that this is the answer. I'm saying by some magic, let's assume that B is 0 is to -5. Then now, if you understand that for a rhombus, the diagonals bisect each other, you will understand that this midpoint here is going to be the same for both lines. Why am I even, let me just do this. Right, so we already had this line, this diagonal, this is a diagonal, right? We already had calculated the midpoint. The midpoint here is going to be, again, it's going to be 0 plus 4 divided by 2 is 2 plus 0 divided by 2, which is going to be 2 is to 1. All right, so this is 2 is to 1. So we know that diagonals bisect each other. So these two lines are cutting each other at the midpoint A here. So we can see this is equal to that. That must also be equal to that. So these two lines have the same midpoint. So you're going to write to us, as the lady had suggested, the midpoint of PQ is the same thing as the midpoint of BR, right? These are diagonals of a rhombus. Diagonals bisect each other. So if we understand that the midpoint is the same for both of them, now we bring back our lovely formulas that I showed you. We know that the x midpoint of BR, now we're looking at this line segment because we're trying to figure out the coordinates of R. It's going to be the x coordinate of B plus the x-coordinate of r divided by 2. We have the x midpoint, which is 2. We have the coordinates of b. I said let's assume that this is 0 is to negative 5. We have the coordinates of b, which is 0. The x-coordinate, by the way, is 0. Plus, we don't know the x-coordinate of r divided by 2. Can you see that we can solve for xr, which is the x-coordinate of r? Can you see that?
Yes, ma'am.
Thumbs up, thumbs down, people. Are you still with me? Yes, okay. So you can solve for the x-coordinate of r by understanding that the diagonals of a rhombus bisect each other, which means that the two lines that cross each other, those are diagonals. The two lines that cross each other at the midpoint have the same midpoint. Similarly, with the y-coordinates, we can say that the y midpoint is equals to the y-coordinate of b plus the y-coordinate of r divided by 2. Y-coordinate of the midpoint is 1, which is equals to, I said let's assume that the y-coordinate of b is negative 5, because we had already calculated it, but I didn't calculate it really. Then y-coordinate of r, we do not know. All of that divided by 2. And then from this, you can see that we can solve for yr, and therefore as to having the coordinates of r. So understanding the properties of these quadrilaterals and triangles, it helps you in such questions, understanding how am I going to solve the question. In this case, the examiner did not tell you anything about diagonals, but you should know, the moment the examiner tells you that that is a rhombus, you should know that a rhombus has diagonals, and those diagonals bisect each other. And what does that mean? That means that the two diagonals will share the same midpoint. And I can use the midpoint formula to actually calculate and solve this question. And that is it. So I am going to post some questions that you guys can work on before we see each other again. What's the surprise you said you had? Oh, I canceled the surprise for some reason. I'm gonna tell you what it was on the group. But yeah, I canceled it out because we're not gonna have time. But yeah, so yeah, are there any questions before I close my session officially? But either way, yes, what was I saying? I was saying I'm gonna send you some questions that you need to practice. Because again, very, very important, analytical geometry, grade 11, because it's a whole question on its own. I'm seeing two hands, yes. Yes,
ma'am. Ma'am,
yes.
about the rhombus question, right?
Yes.
Is it safe to also use the method whereby you see we were given the BQ, right?
Yes.
So can we calculate from like the x from B to Q, it's +4, and from the Y's from -5 to 0, you add 5, and then you use it with the P. Do you get what I'm
Yes,
trying to say?
you can do that. We call it inspection. You can solve the question by inspection, because we know that part of the properties is that this line is parallel to this one. So if these two lines are parallel, if I'm moving from this line B, if it takes me 4 units to get to this point, ideally it should also take me 4 units for the other one to get to the other point. So that should be 4-ish also. And then for the y coordinates, if you know that moving from B to Q, it should take you, if this is -5, it means that it's going to take you 5 units to get to 0. So it should also take you 5 units to move from P to R in the y direction. So it should apply. In case
Thank you,
someone is
ma'am.
no worries. In case someone is confused, she was just asking about inspection, which is where you don't have to do a calculation really. You can solve for the answer by looking or understanding the fact that if these two lines are parallel, there's just too much on my sketch going on. Oh my gosh. Let me just remove everything and just show you properly, because I know probably some people are interested. So if I have my rhombus like this, guys, if I have my rhombus like this, right, We know that for a rhombus also, it's not only about the diagonals bisecting each other, but also the opposite lines are parallel. Other than being equal, they're also parallel to each other. So what she was saying was that if I know that B is 0 is to -5, right? I can say, let me draw a line parallel to the x-axis like this here, and ask myself, how much does it take, or how many units does it take to move from B, let me just use this, how many units does it take to move from B to Q? And that is taking 4 units. How do I know? The x-coordinate of B is 0. The x-coordinate of Q is 4. So it means that it takes me 4 units to move horizontally to get to Q. Then you also ask yourself, how many units does it take you to move vertically, to move from B to Q, like this? We know that B is at -5, so I need to add 5 units to get to the y value of Q, which is 0. So we know that this is 5 units going up to get to Q. It's like you're asking yourself, how can I shift the point B to get to Q? You will have to shift it 4 units to the right and move it 5 units upwards to get to Q. Because the two lines are parallel, because this line is parallel to, let me just show you, because this line is parallel to this line, what is happening to the line PQ must also be happening to the line PR, right? So for the line PR, if I do the same thing where I draw a line that is parallel to the x-axis like this, a line that is parallel to the x-axis like this, it should also take 4 units in this direction. It should also take 4 units in this direction. Sorry, as it did for that one. So this should also be 4 units. And then moving from here, going up, it should also be 5 units, which will basically tell us, moving from P 4 units, that will tell us that the x-coordinate of R is 4, because you're moving 4 units towards the right. And then if you are moving from this y value of 2 and you are moving 5 units upwards, that should land you at 7. So then you find out that the coordinates of R are 7. So that is a method called by inspection. So whenever you do it, just write next to it by inspection. And then that will technically be it. But other than that, that is it from me. If there are no other questions, let me check first. I'm not seeing any hands. Yes, so if there are no other questions, I will see you tomorrow, guys. I might change our session from being facilitated to being live. But I will let you know if I do, because I can see that the June exam stress is catching up to some people. So I will just try to make it a live session so that we can get through content much more quicker, so that we can finish earlier and have time to revise some things if we can. But yeah, other than that, guys, good night and keep warm because it's very cold, especially people in the Western Cape. Oh my goodness, it's very cold. It's excruciatingly cold. So keep warm, guys, because you need to write your June exams as healthy as possible. You do not want to be coughing. On the other hand, you're not seeing the angle of inclination. On the other hand, you're not seeing Euclidean geometry. So keep warm and make sure that you're as healthy as possible for your exams. And I will see you when I see you for our next session tomorrow. And I hope that you learned a thing or two. And that is it.